Alright, let's go ahead and get started. So, welcome to the seminar on Foundation. The goal of this set of lectures is to try to tackle some of the foundational questions that arise naturally when studying mathematics. So, I know from personal experience, at the very least, when I first learned about axioms and axiomatic theories, I felt very angry, hurt, confused even. I was like, what is an axiom? How do we know that it's true? How can you not argue it? Like, what does it mean? Do we prove these things? Do we assume them to be true? Is that really valid for a foundation of all our science and knowledge of the entire universe? I think another entrance into these kinds of points of confusion is in category theory. Once you start describing the collection of all sets, for example, and you run into the famous sentences, size issues with such concepts. There are indeed fixes to such things, but they're not exactly straightforward, and sometimes they can be a little bit confusing, or they can even be skirted over in some courses. So we wish to tackle these questions, make the answers to them transparent. Billy and I, so Billy is also partaking in these lectures, we hope to also discuss some of the philosophies, some of the points of confusion that we came across, and hopefully come to some answers. Ultimately, throughout this lecture series, we also want to discuss and prove Gödel's incompleteness theorem, so eventually we'll get to that as well. Okay, but we're going to start right from the very beginning. Today's lecture is simple. I'm just going to be presenting the definition of a first-order signature, followed by a first-order theory, and then I'll do a very simple example of such a thing, and then I'll discuss what it means to have a model of a first-order theory. So a very famous example of a first-order theory is set theory. A lot of people understand this as a foundation for mathematics, and so how do we define set theory? Well, it is a first-order theory, and that's what I'm about to define. So we're really starting right at the very, very beginning. Let's begin with the definition. So this is going to be a first-order language. First-order signature consists of the following data. So we have a set sigma sort, the elements of which will be sorts. And then for each sort, we're also going to have a countably infinite set of variables. Countably infinite. We'll assume. I'll introduce a little bit of notation here as well. I'm going to write x of type A for x being an element of the set. So x being a variable associated to the sort A. Okay, we also have another set of function symbols. I can't draw symbols. Associated to every function symbol is its type. a set simplified function symbols together from that assigning each function symbol. Right. So, alright. A type is going to be a finite set of sorts. And so the notation is f a1 cross dot 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 cross a n to b.
You mean a sequence of sorts?
Yeah, I'm thinking a sequence of sorts. Order is important and you're allowed repetition. Okay, and let's move to the boards now. Okay, so I'm still going with the same definition. We also have another set of relation symbols. Relation symbols also have an associated type, which is another finite sequence of sorts. I'll introduce notation for this as well. Okay, good. So that's the end of my definition. That is what a first order signature consists of. So I'll just mention briefly that the way that I wrote the notation for the function symbols and also the relation symbols are quite suggestive. But at this point in time, it is purely syntactic, right? So the cross that you see inside the notation for a function symbol does not mean Cartesian product or categorical product. It doesn't mean anything like that at this point in time. It is just completely empty syntax right now.
Mm-hmm. Perhaps we should also just reflect on a bit of the definition from the first board. Could we go back over there?
Yeah.
Oh, yeah. The orbs falling.
Yeah.
So, yeah, I just had this thought that, when you wrote x colon a means x is an element of the set VA, it sort of sounds like that's a sort of logical sentence, that's a sort of assertion that you could make, and it kind of strikes me as more of this is a typing thing to indicate to to the author or the reader of a sentence that what the types of the variables are, rather than it's not the kind of thing that the logic is for, to conclude that x is in this set of variables or it isn't in this set of variables or something.
Sure. So, I mean, by X colon A means X an element of the A, I absolutely don't mean implies in any sense of the word, not mathematically, not within some system. Is that the concern of this notation, that this could be read as implies in some way?
I just mean that you wouldn't say like we're gonna have like a conjunction operation. We wouldn't say like X colon A and like P implies Q or something. Like it's not within the language.
Can we just say it like this? The idea of sorts and to have a sort A is more or less to have an agreed upon convention that some symbols on the page can be associated with A and others not. There's not really a set or anything else. It's like a syntactic recognition agreement among the people reading the page, something like that.
Right, yeah, I think that's a good way of putting it. We should also make the comment about the countably infinite set of variables, that it's a matter of being able to produce a unique variable at any point in time, which...
Can I just let me go off quickly, Billy? We can get into this now if we want, but I have a spot for the talk allocated to this discussion. So I was planning on getting the whole thing out, and then once it's like formally defined, we can then look at it and point to some of the conflicting aspects of it. Or we can do it now, I don't mind, but just letting you know that I did.
We can do it later.
Okay. Cool, let's go back to the other board and define terms. Okay. So associated to every first order signature is a collection of terms and relations. And these are the next two definitions. So the collection of terms is an inductive definition. I'll describe how to construct the set of terms. Smaller set subject to the following. So terms are relatively simple. Formulas are a bit more full on. The variables, all terms, and then anything that we can construct using the function symbols in a way that is in agreement with the type of the function symbols is a term. Let me write that out.
Do you have a motivating example for like how we should think about terms and function symbols? Like,
do I have a motivating example? I mean,
or do you want to discuss one here or move on?
well, sorry, I've got something else in my mind. Let me address that in just 1 second before I forget. I didn't make it clear that associated to every term is also a type. So associated variables of type A is the term, which is that variable, but that term is also going to be of type, the same type as the variable. So let me write that here. Of type A. And then down the bottom, I did mention that for the function symbols. So once we apply a function symbol to appropriate terms, we get a new term, and that is of type B. That's what the special distinguished final element inside the sequence of sorts that describes the type of a function symbol is there for. Okay, going back to Billy's point. So a motivating example, I'm not sure what you have inside your head. Like, it depends on what aspect of this that you're looking at. If you were to try to interpret such a language, then the absolute most obvious canonical example is to do so inside the category of sets, where all of the symbols mean what they look like they mean. So I'll just think of a function symbol as a set theoretic function inside that semantics. Versus if you were to think about it more term constructively, then maybe I would think about it as a stronger typed language like Haskell, but I'd need to make a few comments in order to make that actually make sense.
I think it's important to be careful about like when we talk about think of like a function symbol f means this or like is this. There's like in one sense you could be talking about what I mean is like in one sense you could be talking about the semantics which actually interprets the function symbol as a function, and so in that sense the thing that it means is the thing that it's interpreted as. But like I think it's also important to think about how should I think about the function symbol on its own, like irrespective of like some particular semantics and interpretation, like because someone could be genuinely asking like what is this thing? How should I think about it? Well, like without a specific interpretation. And I sort of think that kind of like definite descriptions, like if I would say, like if we're talking about a variable x of some sort, and maybe the sort is like all people or something, and I have a one place function symbol which was like the mother of or something. But like what I mean there is sort of like in our language we use the word like the mother of as a way of sort of like we're referring to some definite description of something, and it's being described in relation to like some like noun, like in this case x, like I could refer to like the mother of a specific person and use their name, but here we have variables.
Is it necessary to go all like real worldy about it? I mean, I think there's a computational interpretation. The meaning of the different types of symbols is how they transform the nature of other symbols when you combine them according to the term formation rules, in my mind. So it's a function symbol is the kind of symbol that when you stick it next to a variable of type sigma or whatever, type A, gives you a term of type B. Like its nature is the nature of the transformations of the types of things that it performs when you write it next to other things. And you need all these particular variants of those kinds of transformations of terms into terms of other types in order to form the theory. I think that is, I mean, that's one way of thinking about it. It's purely at the level of the computation of how the types of things changes on the board.
Mm-hmm. I think good point as well. I guess what I'm getting at is that is also just baked into the fact that f of something is a term, so it's one particular thing. It's not like something that could be thought of as many different terms at once. But yeah,
a distinction between f of t1 dot 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 Tn and the collection consisting of that plus the terms that created it. Is that what you mean?
sorry, I didn't quite catch that.
So it sounds like you're drawing a sharp distinction between the term, which is f of t1, comma, dot, 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 comma, tn, right, as one term. You're distinguishing between that and the collection that consists of that term along with the terms t1 up to tn that were used to create that term.
I'm not quite sure I follow like what the collection is. But
just f of t1, comma, dot, 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 comma, tn, and t1, t2, t3, dot, 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 down to tn. So it just sounded to me like you wanted to draw a point that f of t1 of t2 down to tn is one standalone term, and it doesn't have along with it the knowledge of t1 up to tn. Maybe that wasn't the point you were making, but I thought that's
maybe sure. I can also make a more simple point that whenever I teach people logic, I notice usually there is a because we use this as because the way we usually think about f applied to some terms is like we're applying a function to some stuff and we get something out as a result, and they think that that this actually creates one of the other terms in this first order signature, like f of t1 up to tn might actually be like the variable x or the variable y or something, but
I see what you're saying.
To be clear, so you can think of it as literally just that syntax on the page. It doesn't become something else. But of course, when you interpret it in some model, that's when stuff actually transforms into being other stuff.
Yeah, okay, that's a fair point. So I think that relates to Dan's interpretation or description of what's happening here, but also kind of the way I think about it. Like I just police myself inside my mind, right? I force myself to swallow the fact that we're only describing syntax at the moment. We don't have meaning to this. We're like formed an agreement of how we can write things down, and that's absolutely it. So there's no way that f of t1 down to tn can be anything. It's just what I've allowed you to write. Okay, shall we move on to the next board and look at formulas?
Yeah.
It's so creepy seeing you guys form on your own ghosts.
Yeah, it's a procession.
I'll confess, I'm kind of into it though. Okay, so as I mentioned, associated to every first order signature, there are terms, there are also formulas. Let's now define the formulas. Relation symbols have associated to them a type, but I'm not going to associate a type to a formula. I'm going to associate something else, the so-called set of free variables. So I'll simultaneously define the formulas along with their set of free variables. Okay, and so there's just a whole bunch of different rules for these. Okay, so given a relation symbol and some terms that are of compatible type, then we can construct the following formula. And the free variables are I didn't define free variables of terms, sorry. So it's the union of all of the free variables of all of the terms. Where the free variables of a term are simply the variables that are used to construct this term.
I suppose since this is foundations, maybe we should at least explain what this union is. So you just take all the collections of free variables, T1 up to Tn, and you gather them into one big collection. That's all that means.
Yeah. Okay. We also have equality, so the equality relation, or the equality formula, given two terms. And we do require them to be of the same sort. Oh. Okay. Yeah, I guess this would be another point to make the similar observation that Billy has been making. So S is equal to T is literally some syntax that I have written down on the page, right? And that whole thing, S equals T, is one formula.
It can be especially hard to read when there's there's an element of symbol after, because people often read that as sort of saying S and T are equal, and by the way, they're both in the set F, but that's definitely not how it should be read.
Yeah, I guess I'm being lazy / there, just slick. Yeah, I should be saying the term S equals T is an element of this set F. And
I didn't mean to say you were being lazy. It's just a matter of like just reading the notation correctly.
Yeah.
Like mentally, like I'm just going to draw some brackets there. In your head, you should pass it like that.
Yeah. But we don't want these brackets as actual parts of the syntax. But yeah, you can read it. You can read it like that. Okay, there are two special symbols, which are named truth and falsehood. That's terminology for them.
I should say in the future, I end up ignoring the truth symbol. And I pretend that the false symbol is the only one, the only special one there. But you can redefine the truth symbol.
Yeah, you didn't present deduction rules for the truth symbol, did you?
No, I didn't, but there's a, like, you can just do it like an axiom rule, so
Yeah,
with no premises and just the truth conclusion.
Mm-hmm.
Oh, I also wanted to point out that your phi and your empty set look the same.
Oh.
Yeah, do the var-phi.
I don't know how to do that with my hand. Okay.
Backslash var-phi, Will. Combine.
Oh, right, I see what you mean. Nah, it's too late for that.
No,
This is
yes.
No, I mean, like, I don't want to go back and change them all now.
Just make the empty set more big and round.
Well, if you guys coded a circle drawing tool, then I would love to do that. Okay, so now I'm writing if phi and psi. Oh, okay. I guess better late than never. Okay. Oh god, I haven't got writing on Roblox down for fine art yet. Okay, and then we allow for. Oh no, my iPad's on my battery. I think it's not charging properly.
Your voice is a
Alright.
bit muffly. Are you
Oh,
away
sorry,
from your mic?
that's me falling asleep at 11 p.m. Alright, let me perk up. So, if phi and psi are formulas, then so are the following, which is just disjunction, conjunction, implication, and negation. Oh, no.
So we're coming up on the end of this time slot, but just to confirm, just continue through the tea break, which is here anyway, so anybody who joins, just come here.
Okay, sure. Great. So hopefully there's nothing too confusing about what I've written here. So this is
Could you
just...
just... Oh, yeah, you're about to explain it. Cool.
Yeah. Yeah, so this is just allowing for the conjunction of two formulas, also the disjunction and implication. So again, this is just raw syntax that we're allowing ourselves to write down at this point. Was there anything that you wanted to add?
Oh, well, so to be clear, what you've written in the bottom right corner is a schematic with a square in place of any of these symbols you've just introduced. And you're saying
Right.
for any of them to take the free variable of the more complex formula, you just take the free variable of the two arguments and gather them together. The free variables, I should say.
Yeah. Yeah, sorry, that was purely because I was running out of board space. So just in all of the cases, the free variable of the relation you've constructed is the union of the two that constitutes it. I've just snuck in negation down the bottom as well. So if phi is a formula, then the negation of phi is also a formula, and it has the same free variables as phi. Nice. Let's write... I'm not finished. I have to do existential and universal quantification. So let's just move to the first board again to write that up.
We
Does look like a lot of fun. Okay. Confirm clear. Good. That worked. Okay, so I'm still continuing with the same definition. We have existential and universal quantification. Okay, then we can construct these two terms as well. Now, the free variables of these terms are it's the reason why we define free variables. So this is the interesting case. So this is important. The free variables in both cases is the free variables of phi, which is a set, and then you remove from that set the element x of type A, of sort A. Okay, and the point of free variables is the non-free variables, right? So the point is that phi is a formula that is consistent of a whole bunch of different variables, and then if I take the universal or existential quantification of one of those variables right at the very start, I bound that variable. It is now related to the quantifier right up the front of the formula. And so that is no longer a free variable. That's why we remove it from the set. But all the other ones that didn't have that happen to them, they do remain free. That's the end of the definition of the formulas corresponding to a first-order signature or a first-order language. Any comments or questions?
I guess we should, along the same lines of explaining these sets as we go, to be clear that there's no, when we're gathering all the free variables of a formula, they're not variable occurrences. So the same, if you have the same variable appearing in multiple spots, we just have that variable itself, like what the variable is. We don't record its position or anything. So in removing x from the set of free variables, we are there's not more than one occurrence of x that we're only removing one of or anything like that. It's all of them.
Mm-hmm. Yeah, so I could write that out as a small example if we wanted. So if we had a relation symbol, let's just make it A. That's the point. Sorry. So this is a valid formula, and it has free variable set. Okay, now it is good. I think. Verify. Free variable set is just the empty set. Okay, good. So this was the part in the talk where I had allowed for us to look at this definition and poke a few holes in it or ask a few questions about it, become confused about it, and provide alternatives. So I think it's a shame that I've erased it now. But I think that the most immediate problem that you run into with this definition is that right at the very start, when we were defining what a first order signature is, we said that it consists of all of these sets, right? We had a set of sorts, we had a set of functional symbols and a set of relation symbols, and associated to each sort, we also have a set of variables, right? Now you might ask yourself, like, what is a set? Like, what does that actually mean, right? If I'm thinking of a set as an object that is defined according to the theory of sets, like Zermelo-Fraenkel set theory or ZFC with choice, then you might say, well, what is ZF? What is ZFC? Well, they're examples of a first-order theory in the first place, right? So how could a first-order theory be defined in such a way that requires the knowledge of what a set is, when a set, once formalized, is nothing but a first-order theory anyway, or an object defined by first-order theory? It appears circular, right? And in fact, what I just said is circular. Like, that is circular, so that's a problem. So how do we explain that? Okay, there are many different approaches that you can take to reaching emotional comfort with this. And I think that part of becoming a mathematician is exactly this journey. What I would suggest at this point in my life/career is that whilst pursuing any kind of theory of knowledge, and literally be that anything, it doesn't even have to be restricted to mathematics or philosophy. I believe the same holds true if you were to study history or linguistics or something. There is always some kind of fundamental notion or fundamental assumption that you bring to the study, to the science that you're partaking in. And that which you bring to it is a core ingredient that is required in order for you to get something out of it. So you end up, like, mathematics is a meaningful endeavor. That's undeniable. But you do need to bring to it some kind of underlying belief/assumption that you can feel comfortable with. So what I would say to you is, it's not necessary that, in fact, we need the set of sorts to be a set as per Zermelo-Fraenkel set theory. I, as who I am, don't think about it in that way. What I say to myself is, we're describing a language with which we wish to perform mathematics. So we hope for this language to be precise, and we hope for it to be non-ambiguous. Which means what we really need is the ability to write down sorts. We need to be able to write down different sorts, and we need to be able to identify when two sorts are the same and when two sorts are different. Now, we can literally think about this as etchings on the page, like what I mark the page with as I write down terms or formulas inside corresponding to a first-order theory. Obviously, that has to be taken up to some kind of equivalence because there is problems with different people's handwriting. But the emotional experience of feeling it to be murky to analyze the difference between people's handwritings, I think, is reflective of the assumption that I bring to mathematics in the first place. I do assume that within this universe we can have meaningful discussions involving syntax. If I can't do that, then I lose absolutely everything. If I insist that when you write the letter A and when I write it, they look different, and so therefore I cannot determine what you are talking about, then I have no ability to extract meaning from mathematics. So what we really need, does someone want to jump in? I've said some controversial stuff.
Can I, just before that, you said something about, we need to assume that we can write down a sort, and like the way that's worded, I don't really know what that would mean. I think it's more like someone might suspect that like logicians do is like construct like all these different fancy sorts, and my impression is that like a sort is like you really just give a name to it. Like we're sort of giving sort of abstract names like A and B, or like A1, A2, as just sort of like, yeah, just arbitrary names for sorts. But there's like in practice, there's not really anything underneath that. It's really, as Dan was saying, just a organizational principle in which like the identity of what the sort is essentially just some kind of marking itself, and there's some procedure by which we recognize particular variables to be of a particular sort. Having said that, that's also kind of a lie, and the way that like we talk about variables being like this variable's of that sort and this variable's of that sort, like we just like throughout we just reuse variables, like the same variable for multiple different sorts, like all the time. Like you could use X as a variable for this sort and that sort. Like that's sort of how I see it being used in practice. Like maybe if you're really particular, you might like mark the like like you might, I don't know, use subscripts and only use like even numbers for like the variables of this sort and odd numbers for the variables of that sort, or something like that. But I'm going on a bit of a tangent, but the sort of X:A is sort of a way to like reuse the same symbol, but sort of pretend it's a different symbol that's like purposed for the sort A.
Mm-hmm. Yeah, for sure. And the point that I want to make is that we could all feel good by sitting in a room and deciding that what we're doing is prescribing abstract names to variables and defining, assuming that we have procedures in order to distinguish variables and stuff like that. But it's just a bit unfair because it's so not what we wrote. You know what I mean? Like this definition that we've presented is this is a set, and here's another set, and here's another set, etc. So I think what I observe every single mathematician do when these definitions come up is absolutely none of them swallow it, It's like they all have some way of describing the way that they've kind of come to peace with this point of mathematics, which is the start of it, right? And I think that that's not to be feared. I think that's to be encouraged. I think that if somebody is watching this and they're studying undergraduate mathematics and they're really struggling over foundations and they just want a proper definition, but they feel a bit too nervous to come up with their own philosophy of it because they're just a little guy, I'd actually encourage them to take those philosophies and those thoughts seriously and engage non-ironically with your classmates, with your teachers, and with people online, whatever you have access to, over that philosophy. I really think that it's a fundamental part of this aspect of mathematics, which is the very beginning of it. Dan is the only mathematician in this room. Does he have anything to say on the point?
Sure. What, like in the sense that I'm blessed by the institutions of society with this title? Is that what you mean? You're both mathematicians, you dork. I just want to say amen to that little speech.
Yeah, you what? Sorry, I missed that last bit. I was bathing in insults. Go again.
I want to say amen to your little speech.
No. Okay, cool.
Can I make a comment about you referring to the circularity of set theory and understanding the definition? I've sort of come to feel that, like, I feel like, so as a person that has had, I guess, some like amount of experience with set theory and logic, I have the feeling that sort of a newcomer to this, if you just describe to them what you mean by a set of things, like as a collection of things in which like you don't like you can't have multiple occurrences of certain things and the order doesn't matter, or some description like that. I feel like they would have no like fears about like saying the word set here. And it's usually only when you sort of inflict on someone the trauma of all the like paradoxes of set theory that they begin to like worry, like wonder like, wait, what is a set? And I kind of feel like all of the problems of set theory are kind of not like have no consequence here. Like that might be a controversial take, but the fact that we're restricted to some, like we're only talking about sets of, like if you prefer, symbols, and like we only need sort of countably many of them, and like essentially in my view the only like insanity that creeps in with set theory is when you are really trying to like form the set of all things that like you, if you want all of the sets to be present in some sense, so that like whatever could be in a set is like present in some set, or like things of that nature, that's when like you start to like doubt yourself about, wait, what is a set? But at this like ground level where like we're talking about sets of like markings on the page up to some equivalence, there's no real like controversy there. There's no real complication, and that's one thing I wanted to say.
Yeah, for sure. I think that you could, in fact, go ahead and define it in that way, though, if you were to. Like, I think it'd be reasonable to define all of this as finite sets. You know, like as associated to a first order signature is a finite set of sorts, a finite set of function symbols, finite set of relation symbols, etc. I think that you won't run into issues practically if you just assume that, in which case all of the paradoxical set theoretic stuff is not really going to actually come up. Is that reflective of what you're saying?
I mean, I think you'd not get far if you had only had finitely many variables, but like as a concession, you can think of having only one variable. And I said this the first time we attempted this lecture, that like you have one variable and like a variable formation syntax or something, where like from any variable you can just produce another variable by like modifying what the symbol looks like adding markings or something.
Yeah, but my point is that you can't even do that countably infinitely, you know? Like, if I have x... I mean, this point came up last time as well. If we had x 1 billion primes, and then x 1 billion plus 1 primes, but like not 1 billion, 1 billion's kind of easy enough. Imagine some big number, then you still can't really tell the difference between them, right? So you still run into issues if you're going to use that many variables. So I think that you actually are limited. Like, if you're going to be real about what you're going to do, you're only going to use kind of reasonably sized sets the entire way. So I think you could just formalize it in that way right from the very start.
Yeah, but I feel like that sort of sounds like you're like restricting the whole like language, or like the whole logic that this is supporting, and sort of pretending it's unable, like there are very, very, very complex formulas that express things in some particular logic defined on this language, and you're sort of pretending that like they're not present in your logical system just because they, like, the way that you would have to inscribe it like is too large or something. I don't know, I don't really understand why like that's a, like, practically you're only going to write down the small ones, but I mean, are we pretending that like the whole universe of possibility of the formulas that are present in the logical system is like limited in that sense?
I like, yeah, I think it would be reasonable to suggest that. I mean, you're limited by what it's a first. You could argue that a first order language, by definition, is limited in that way. It's not part of the language because it's not part of the availability of our utterances and of our writings, which might be what you're trying to do with this definition. You might be trying to formally define what it is that we are able to communicate.
Yeah, I don't know what more to add to that because I don't really get this
I mean, yeah, that's
line
the
of
fun of
reason.
it. Let's get our bearings for 1 second. It's 11:20 and I'm worried about my neighbours. I don't want to be too disruptive to them. Could we call it a place to finish there? I could even come back later in the day for you guys, just once I wake up or something. What do people think?